And when you then go to the term linear models, all they're doing is saying word problems that involve linear equations. So when you hear the term linear models, they're just talking about modeling a real life situation with a linear equation. So the first real life example they give us here is in example 1. Jacksonville, Florida has an elevation of 12 feet above sea level. Hot air balloon taking off from Jacksonville rises 50 feet per minute. Write an equation to model the balloon's elevation as a function of time. Graph the equation, interpret the intercept at which the graph intersects the vertical axis there. So if we are looking for the balloon's elevation, which is what they have here, we would have to say, well, it's the how fast it's going up times how long it is traveling that fast. But then we have to add how high it started to begin with. All right? So when you look at this, this is really a linear equation. Y equals, my rate is m, my time is x, my y-intercept is b. And so when we do this, if we were to say, well, let's plug in and see what we have. We don't know the balloon's elevation. They did it with h, I'm assuming for height. We do know how fast it's going up. How fast is it rising? According to this problem. Yeah, so it is rising at a rate of 50 feet per minute. Do we know how many minutes? Have they told us? No, so we need a variable there. All right, they use t for time. We do have to consider where it started. What is its starting elevation? 12, because that's the elevation of Jacksonville, Florida. All right, so this is a linear equation, right? Y equals mx plus b. If I were to do this graph here, again, I probably would not do it in individual units. Now, when you're doing a word problem like this, keep in mind you're not actually talking about x and y. You're talking about time versus height. And so if you label one side with height and one side with time, the units don't have to match up. All right, so if I wanted to, when you do this, you do need to label it, by the way. So if I'm labeling this, I'm going to say, well, this side right here is my height. This side right here is my time. And I could legitimately do, 1, 2, 3, 4 here. And I could do 10, 20 here. You do not have to use the same units when you're talking about a rate of change, because that automatically indicates that I have different units. So go back to where you came from, little guy. So when you're doing this, you don't have to label them exactly the same. And so just make sure that whatever you do, you note it on the graph that you have done it that way. And that way I know what you did, and everybody else, if they were to look at your graph, knows what you did too. Let me fix him. He's all crazy now. All right. So when you're doing these, make sure you label that we have time here, and you probably want to say exactly what it is. Time in, let's say, minutes, right? So time in minutes, and height, and we would say like feet. All right. And then it says to graph it. Well, we can graph this just like we would anything else. We start at 12. That's probably going to be about right here. And my rate is 50 over 1. This is why I wouldn't want my units at bottom to be the same, because if these were 10 and I had to go over 1 unit, that would be really hard. So if I go up 50, well, that's going to be around 62, and over 1, that's going to be about right there. All right. And then, of course, you draw your line to connect it. You'll notice again that I don't go below that 12. Now, with elevation, you actually can go into the negative, right? You can have a negative elevation. That's not unheard of. But in this situation, they've told me that the elevation of Jacksonville is 12. So it's not going to go below that. On the X side, we cannot go negative on the X side. Why couldn't we go negative on the X side? Right. We can't time travel, okay? So my minutes are only going forward, not backwards, right? And this represents this particular graph. It says, then it wants us to interpret the intercept. Well, the intercept, we've already said, 12 represents our starting elevation, right? That's where we started from. So any questions about just representing a function with a graph? All right, you are going to try one. Check understanding. Suppose the balloon, and they change it a little bit. So if you look at this one, pay attention to the terminology here. Descending, that's going to be a negative rate. So a negative rate of 20. The initial elevation, that is still a positive 1350. And so you do have to kind of estimate. I did it by 200s just because it was such a big number. I mean, you could have done it by 100s if you wanted to. You just have to have 13 spots there. And then I also estimated when I did down 20 and over 1, that was an estimation as well. So the first way that they can give you a linear model is by somewhere in the description giving you the slope, giving you the y-intercept. They're basically giving you some rate of change and then some starting point or something that you're going to add to it. Another way is they can actually give you 2 points. You think of these points as an XY and an XY. That's the situation here. A candle is 6 inches tall after burning for 1 hour. After 3 hours, it is 5.5 inches tall. Write a linear equation to model the height of the candle, which they gave you as Y, after burning X hours. So what did they just tell you? They told you, well, height is Y, hours is X. So pay attention when they give you variables because they're kind of giving you a hint as to what's going on here. So that means based on what they just told me there, I have a Y here. Went too far down. I have a Y here and an X here. I have an X here and a Y here. So they've given me 2 points. They've given me after 1 hour, it is 6 inches. After 3 hours, it is 5.5 inches. And they want an equation. They've given me 2 points. How do I find an equation if I have 2 points? I need the slope. And I need the y-intercept. So once I find the slope, I can use point slope because I have 2 points to choose from, right? And then there we go. This one goes on top. All right, 1/2. That's easier. There we go. Yeah, so this is my slope. I can use either one of these. I would choose this guy personally. I mean, it's up to you, but I would choose him. So point slope, what does that look like? Y minus, y1 equals m. What we finally determined was our m. X minus, what's x1? Yeah. So you are going to have to manipulate fractions a little bit here. Negative 1/4 x plus 1/4. What happens here? Add 6. You can leave it. I don't know if they left it as a mixed number, but you can. Just because we're talking about height, 6 1/4, that actually represents our inches, how tall the candle was initially. This is the reasoning. What is the slope? Negative 1/4. What does that represent? How fast this is burning. So it is losing 1/4 of an inch every hour, according to this, right? Every hour. What does the 6 1/4 represent?
Where it started.
Yeah, so how tall the candle was initially. The candle was initially 6 1/4. It says another candle is burning, is 7 inches tall, and it's burning. So go ahead and do this one right here. Answer C by yourself. The next thing we're going to do is we are going to be using a linear model. So we just use the equation from example 2. So the equation that we had was y equals negative 1/4 x plus 6 1/4. So now that we have that, we can then predict things from it. When will the candle be 4 inches tall? Which variable does 4 inches tall represent? The x or the y?
The x.
Yeah, so remember, y is height, right? Y was height and x was time, remember? So they're saying, when will the candle be 4 inches tall? They gave us the height. So we're going to plug 4 inches into this part of it. And so how do we solve that? We plug it in, and now what do we do? What's our first step? Let's not jump. What's our first step? Yes, subtract 6 1/4. All right, negative 6 1/4 and positive 4 give me what? All right, keep, change, flip. I do need to change this guy first, right? What is negative 2 1/4 as a improper fraction?
Negative 9/4.
Negative 9/4 equals negative 1/4 x. Multiply both sides by negative 4. Right? I'm going to get what? X equals, stop jumping. X equals 9. You know. So x equals 9. What does that tell me? What did that just tell me?
Your height? Or how long will it take?
When will the candle? After how many hours?
9.
After 9 hours. All right, so I feel like a little bit of this is struggling with knowing what we're being asked. I wrote this out. When you have a word problem, it's kind of important that you do that. Twofold. If you're setting your own variables up, I need to know what variables mean what for you, because I'm not in your brain while you're taking your test, okay? 2, when you get to a secondary question in a word problem and you haven't defined yourself what those variables are, you may forget in the middle of solving the problem. So define your variables and go back to and make sure that you're plugging it in for the correct variable. And then also when you get your answer, make sure that it makes sense based on what you said your variables were.
So could the
Scatter plot. So top of page 80 here. Scatter plot is the graph that represents two sets of data. By plotting the data as ordered pairs, you can use the scatter plot to determine a relationship between the data sets. This is often used in business because, as you know, life is not a linear model, right? I mean, it's not always perfectly linear. And so what they will do is they will plot two different things to see if there is a correlation between them. All right? There can be a weak positive, strong positive, weak negative, strong negative, or the last one, no correlation. Positive meaning it's going up from left to right, negative meaning it's going down from left to right. This is a good thing to do actually in life. When you're presented with stuff, it has to be, is there a correlation between what they're presenting to you? And so businesses will do this like with price point and cost or something, and say, okay, let's look at our price point and cost, and let's find the best kind of price to set this at, cost versus how many people are buying it. Because there's going to be a correlation. If they set a price too high, you're going to see fewer people buy it. If you set a price really, really low, lots of people are buying it, but they're not making very much money. So they want that sweet spot where a lot of people are buying it and they're still making money. And so they're going to use something like trends here. Trends change though. All right. So if you look at trend lines, something can get thrown in the middle and it can change it. This is really just to see, is there a correlation at the moment? And that trend line, which is what I'm referring to, is what the line would be if you were to draw one. So if I were to take this and draw a line through here, right, that would be kind of the model that I would use. Obviously, they don't all fall directly on my line, but I'm trying to get somewhere in the middle that kind of represents that group of information by a linear equation. Because I can't write an equation on a scatter plot. There's no equation to be had. But if I draw a trend line for that scatter plot, I can write an equation for that, which means as a business owner, I can then project what might happen if this trend continues. All right, so if I'm looking at a trend that's happening, I can project it off of a linear equation, just like we did with the candle. We projected that it would burn at the same rate. Now, anything could happen, right? You could cut a fan on next to it that causes it to burn faster, or to burn not at the same slope as what it's burning at right now. So things can happen to change it, but based on what I have historically, I can project what might happen going forward. And that's the whole point of having a scatter plot and a trend line. She's considering buying a 1993 car shown in the photo. By the way, after 25 years, I think they're considered a classic. So just saying. I don't know. The first thing you'll notice is, just like I said when you're doing a graph, we have years since 1990. So they had to define that. So 1993 was represented, or 1994 weather was represented by a 4. So these are the number of years since 1993. 4, 5, 6, 7, and 8 are since 1990. So that's what the 1, 2, 3, 4. And then the price in thousands. They didn't write the thousands. They just told me it was in thousands. So this 3 represents $3,000. The 6 represents $6,000, and so on and so forth. So be very specific when you create these graphs, that everyone knows what your points represent and what your axis represents for you. All right, so there's a trend line. This looks like a positive, pretty closely done trend line. This would be a strong one, right? It seems that the newer the car, the higher the price. Well, that seems logical, right? And then you'll notice that they didn't go prior to 1994. But if they kept going, this trend line actually may change. Okay? So if you ever looked at vehicles, there comes a point where, like whether it's a 1990 or a 1994, those kind of mellow out to almost a plateau, right? Because if it's in working condition and it's the engine drives and everything else, then you're probably going to get $1,000 or so for it, no matter how old it is, right? And so they tend to plateau. So this is a trend line that if they went back this direction, probably would not keep going in a linear way. It would actually kind of plateau here. But from what we can see here, there's a trend line. All right, it says draw the trend line. So if I were to do that, I would just pick the best representation. Now, I will say when I draw a trend line, I try to make sure that I hit at least a couple points on the lines, so that if I have to actually draw a linear model, I can pick up a couple of them to do it from. So if I were to draw a trend line, I would say, well, this is almost directly on it. And then this guy right here is almost directly on it. So if I draw a trend line, I can then take those 2 points and make an equation with it, right? So I can actually take the 4 here with whatever this is. If we were to make a note of it, that's probably the 5784 there. And then if I were to take this one right here, that's the 7. And that's probably going to be the 9127 there. I could take those two and I could actually take those as 2 points, an X and Y and an X and Y, and do exactly what we did with the candle. And I could take what we did with the candle and I could draw and make an equation out of this from this scatter plot, right? But you have to draw a trend line to do it. And so that's what they've done. Their equation came out to look like this: 1.3x plus 0.2. Remember, those are in thousands and in years. A fair price for x equals 3, or a car in 1993, they said would be about $4,100 based on their trend line. All right. And so if you see how my trend line was going, I was actually, based on what I did, I was barely below the 4,000 mark. So my trend line might actually be a little bit different. When you're doing these, you'll find from one person to the next would have a different equation, because the way you draw the trend line is going to affect which points you put on there and what your slope and all ends up being. So she could project 4,100. I might project 3,900 based on mine. But those are all valid assumptions based on what we have and the information that we have. Just know that trend lines can change. Other things can come into a factor and it can change, or how you estimated it could be different based on what you saw versus what somebody else sees when they do that.